What if I told you there are some pretty horrible blue planets hiding out in deep space? You might think, no way, there are only 8 planets in the solar system and none of them are blue. But hold on, because we're talking about deep space, where even time and space get freaked out and black holes run the show. You're probably wondering, how deep can we go in space then? What's this blue planet? Are there aliens chilling there like we do on Earth? Hey, relax. Don't stress out your brain cells when I'm here to break it all down for you. Today, we're diving into the weirdest, wildest corners of the universe, and I'm going to spill the cosmic beans about mysterious things hiding out there that you've never heard of. They're bizarre and, yes, a little bit terrifying, so watch this video at your own risk. You've probably heard that our solar system has 8 planets, all neatly orbiting the sun. It's a pretty standard setup. But what if I told you that if we travel in deep space beyond Neptune's dark and cloudy atmosphere, things get a lot more interesting? Out there, we find rogue planets. Yes, you heard me right. Planets gone rogue. These planets, also known by their fancy names like interstellar, free-floating, nomad, or orphan planets, are the rebels of the galaxy. They don't play by the rules. Unlike the good old planets that stick around their stars, rogue planets are the cosmic drifters. They wander through the galaxy without being tied down to any star. These planets come in all shapes and sizes. Some might be tiny, others as big as a few Jupiters, but they all share one common trait, and that is they're unbound by any stellar system. And don't think they look similar to familiar planets like Jupiter, Saturn, or Mars. Instead, they have very peculiar characteristics. Rogue planets can range from sub-Earth sizes to several times the mass of Jupiter. Imagine a planet that's 10 times bigger than Jupiter just chilling out there on its own. Because they don't have a star to keep them warm, these planets can get pretty chilly. However, some might still retain heat from their formation, or have internal heat sources like radioactive decay, keeping them toasty. These planets might have thick atmospheres too. Without the sun's rays, their atmospheres could be quite unique compared to those orbiting stars. Now let me introduce you to one of the coolest rogue planets ever discovered, and it is named CFB 2149. Yeah, the name's a mouthful, but bear with me. This rogue planet was spotted by some super smart astronomers using the Canada-France-Hawaii telescope and the European Southern Observatory's Very Large Telescope. It's just hanging out about 100 light-years away from Earth, making it the closest free-floating planetary mass we've found so far. CFB 2149 is like a teenager in planetary years, estimated to be between 50 and 120 million years old. It's got a sizzling surface temperature of around 400 degrees Celsius, 752 degrees Fahrenheit, and weighs in at 4 to 7 times the mass of Jupiter. These details ruled out the possibility of it being a brown dwarf, which is a fancy term for objects with a minimum mass of 13 Jupiter masses. Because it doesn't have a bright star nearby, researchers can study its atmosphere in unprecedented detail, giving us a sneak peek into what other exoplanets might be like. But wait, there's more. CFB 2149 is part of a cool club called the AB Doradus Moving Group. This group is like a stellar fraternity, with around 30 stars sharing the same age, composition, and motion through space. This connection helped astronomers figure out the age of CFB 2149 and confirm it's indeed a planet, not a star. But you might wonder, are these rogue planets also a product of the Big Bang? If not, then how did they come into being? There are 2 main theories. The first one is like a cosmic drama. During the early stages of planetary system formation, things can get pretty chaotic. Gravitational interactions between planets can become so wild that some planets get booted out of their system, turning them into rogue planets. It's like being evicted from the planetary club. The second theory involves close stellar encounters. Imagine 2 stars having a close encounter, and in the process, 1 or more planets get flung into interstellar space, becoming rogue wanderers. Another intriguing idea is that some rogue planets might form all by themselves like lone wolves. These are called sub-brown dwarfs. They form from collapsing clouds of gas and dust in interstellar space, but they don't have enough mass to start nuclear fusion like stars do. Here's where it gets even crazier. Rogue planets might be as common as stars in our galaxy. Surveys like the microlensing observations in astrophysics and the optical gravitational lensing experiment suggest that for every star, there could be up to 2 rogue planets. That's right. There could be billions of these cosmic drifters out there. This abundance challenges our understanding of planetary formation, showing that the universe is even more efficient at creating planets than we thought. The existence of rogue planets has huge scientific implications. They provide valuable data for refining theories of planetary formation and evolution, showing how dynamic and chaotic planetary systems can be. And who knows, these rogue planets, with their internal heat sources and thick atmospheres, might even harbor some exotic forms of life. You might think there are only two types of planets out there: the regular ones we see in our solar system and the rogue planets drifting through space. But hold on to your telescope, because the universe loves to surprise us. Just when you thought you had it all figured out, along come the exoplanets, planets that orbit stars outside our solar system. These cosmic oddballs have turned our understanding of the universe upside down since their first confirmed discovery in 1992. Now we know of over 4,000 confirmed exoplanets, with thousands more waiting for their moment in the spotlight. Each new discovery teaches us something new about how planets form, what they're made of, and the wild conditions they endure. Let's rewind to the early days of exoplanet discoveries. The first confirmed exoplanet, 51 Pegasi b, was found in 1995, orbiting a star much like our Sun. This gas giant, about half the mass of Jupiter, revolutionized astronomy by proving that planetary systems exist beyond our own. To find these distant worlds, scientists use methods like the transit method, where a planet passes in front of its star and causes a slight dimming, and the radial velocity method, which detects wobbles in a star's position due to the gravitational pull of an orbiting planet. Why are exoplanets such a big deal? Well, for starters, the variety is mind-blowing. We've found hot Jupiters, super-Earths, mini Neptunes, and even some Earth-like planets. This diversity challenges our old models of planetary formation and suggests that our solar system might not be the norm. Plus, discovering exoplanets in the habitable zone, where conditions might allow for liquid water, is crucial in our search for extraterrestrial life. If we can find planets with the right conditions, we can focus future missions on detecting signs of life. Some exoplanets are particularly peculiar and offer fascinating insights into planetary science. Take Kepler 413b, for example. This planet has a highly tilted orbit, causing its seasons to vary dramatically. Imagine living on a planet where the axial tilt can change by 30 degrees over 11 years. To make things even more interesting, Kepler 413b orbits a binary star system, leading to an even more chaotic climate. Then there's HD 106906b, which orbits its star at a staggering distance of 650 AU, astronomical units. That's 650 times the distance between Earth and the Sun. This extreme distance challenges our theories about how planets form and stay stable. Its highly eccentric orbit suggests it might have been influenced by interactions with other planets or even a passing star. Another oddball is WASP-12b, which completes an orbit around its star in just over a day. This ultra-short orbit means it's incredibly close to its star, resulting in extreme tidal forces that distort the planet into an egg shape. The intense radiation heats the planet to around 2,500 degrees Celsius, causing its atmosphere to expand and possibly even escape, making it one of the hottest and most volatile exoplanets we've found. Studying exoplanetary atmospheres gives us critical information about their composition, weather systems, and potential for habitability. Using spectroscopy, scientists can analyze the light passing through or reflecting off a planet's atmosphere to identify the presence of various gases. Discovering water vapor, methane, carbon dioxide, and even potential biosignatures in these atmospheres offers clues about whether these planets could support life. Observations have also revealed dynamic weather systems on exoplanets, including high-speed winds and extreme temperature variations, which significantly affect their habitability. The habitable zone, or the Goldilocks zone, is the region around a star where conditions might be just right for liquid water to exist. Finding planets in these zones is a big deal for the search for life. Some exoplanets might even have extensive oceans beneath thick atmospheres or ice layers, similar to Jupiter's moon Europa. These oceans could provide stable environments for life, protected from harsh surface conditions. Space missions like Kepler and TESS have been game changers in the hunt for exoplanets. Launched in 2009, the Kepler mission discovered over 2,600 confirmed exoplanets and thousands of additional candidates. Kepler used the transit method to revolutionize exoplanet science, finding planets like Kepler 22b, a potentially habitable super-Earth, and Kepler 10c, a mega-Earth with a rocky composition. Following in Kepler's footsteps, the Transiting Exoplanet Survey Satellite, TESS, was launched in 2018. TESS is designed to cover almost the entire sky, focusing on bright, nearby stars to find exoplanets that are easier to study in detail. TESS has already discovered hundreds of exoplanets, including some Earth-sized planets in their stars' habitable zones, like TOI 700 NED, an Earth-sized planet orbiting within the habitable zone of its star. Sure, rogue planets and exoplanets are out there drifting through deep space, minding their own business. But even these wanderers have something to fear, and that is the ultimate cosmic monster that can devour anything in its path. Yep, I'm talking about black holes. These mysterious entities have gravitational fields so strong that not even light can escape. First up, we've got stellar black holes. These guys are born from the dramatic deaths of massive stars. Imagine a star more than 20 times the size of our sun running out of fuel, throwing a tantrum and going supernova. The leftover core collapses into a black hole. These stellar black holes are like the compact cars of the black hole family, small but incredibly dense. Their event horizons are only a few kilometers wide, kind of like cramming the entire mass of the sun into a space the size of a small town. Talk about a cosmic compact. Next, let's meet the heavyweights termed as supermassive black holes. These giants sit at the centers of most galaxies, including our own Milky Way. The supermassive black hole at our galaxy's core, Sagittarius A*, weighs in at a whopping 4 million times the mass of the sun. These black holes grow by eating up gas, merging with other black holes, and consuming anything that wanders too close. They're like the sumo wrestlers of space, influencing the entire galaxy with their gravitational pull. Now let's talk about the elusive intermediate black holes. These are the middle children of the black hole family, with masses ranging from hundreds to thousands of times that of the sun. They're rare and hard to find, like the Bigfoot of the cosmos. One of the few confirmed sightings is in the globular cluster 47 Tucanae, weighing around 2,200 solar masses. It's like finding a cosmic unicorn. But wait, there's more. In 2021, astronomers hit the jackpot by discovering a record-breaking black hole in a dwarf galaxy called RGG 118. This black hole, with a mass of about 50,000 suns, is one of the smallest supermassive black holes ever found. It's like finding out your chihuahua is secretly a superhero. This discovery shook up our understanding of black hole growth, suggesting even tiny galaxies can host these massive monsters. So how do we spot these cosmic beasts? Well, there are two main methods: gravitational waves and electromagnetic observations. Gravitational waves are like the ripples in a cosmic pond caused by black hole mergers. In 2015, the first direct detection of these waves, known as GW 150914, confirmed a major prediction of Einstein's theory and opened up a new window into the universe. On the flip side, electromagnetic observations use X-ray telescopes like NASA's Chandra X-ray Observatory to catch black holes in the act as they devour matter. It's like having a front row seat to a cosmic crime scene. Black holes don't just sit around looking menacing. They actively shape their galaxies. Yes, you heard it right. Almost every large galaxy has a supermassive black hole at its center, playing the role of the cosmic boss. When these black holes feed on nearby material, they power active galactic nuclei, AGN, and quasars, releasing immense energy and influencing star formation. They're like the CEOs of their galactic neighborhoods, keeping everything in check through powerful feedback mechanisms. When galaxies merge, their central black holes can also merge, forming even more massive black holes. This cosmic dance leads to bursts of star formation and major changes in the galaxy's structure. Observational evidence, like the high-resolution image from the Event Horizon Telescope, has even given us a glimpse of a black hole's event horizon in the galaxy M87. It's like getting a selfie from a cosmic monster, and it lies so deep in space that it was the most difficult task for scientists to discover. Now, would you believe me if I told you that there are some big bosses, even bigger than black holes? Yes, something so mind-blowingly mysterious that even the most advanced telescopes leave scientists squinting in disbelief. We're talking about dark matter, the invisible puppeteer that makes up about 95% of the universe. Dark matter is like the universe's ninja. It doesn't emit or absorb light, making it completely invisible to us. Yet, it exerts a powerful gravitational force, playing a crucial role in the structure and evolution of the cosmos. Think of it as the universe's secret glue holding everything together. So, what exactly is dark matter? Unlike ordinary matter composed of protons, neutrons, and electrons, dark matter doesn't interact with the electromagnetic force. This makes it impossible to see with traditional telescopes. Scientists have proposed several candidates for what dark matter could be, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. But so far, we haven't been able to catch any of these elusive particles in the act. Dark matter's main job is to act as the cosmic glue holding galaxies together. Without its gravitational pull, galaxies wouldn't have enough mass to keep their stars from flying apart. In the early universe, dark matter's gravity helped pull together ordinary matter to form the first stars and galaxies. It's like the scaffolding of the universe, forming a cosmic web that defines where galaxies and galaxy clusters end up. The first clue that dark matter exists in deep space came from galaxy rotation curves. Back in the 1970s, astronomer Vera Rubin noticed something odd. Stars at the edges of galaxies were moving just as fast as those near the center. According to the laws of physics, this shouldn't happen unless there was a lot more mass present than what we could see. This unseen mass is now known as dark matter, forming massive, invisible halos around galaxies. Another piece of evidence comes from gravitational lensing, a phenomenon predicted by Einstein's general theory of relativity. Massive objects like galaxy clusters can bend the path of light, creating a lensing effect. By observing how light from distant stars and galaxies gets distorted, scientists can map out where dark matter is. One famous example is the Bullet Cluster, where the separation of dark matter from ordinary matter during a collision provided strong evidence for dark matter's existence. Recent discoveries have taken our understanding of dark matter to new heights. Advanced simulations and observations, such as those from the Dark Energy Survey, DS, and the Sloan Digital Sky Survey, SDS, have revealed the intricate structure of the cosmic web. Dark matter forms dense nodes and filaments, creating a vast network that spans the universe. Projects like the Hypersuprime CAM HSC survey on the Subaru telescope have used weak gravitational lensing to create detailed maps of dark matter distribution. These maps show how dark matter clumps together on cosmic scales, providing insights into its behavior and influence. Studies of galaxy clusters have also shown that dark matter makes up the bulk of their mass. Observatories like Chandra and XM Newton have revealed that the hot gas we see in X-rays accounts for only a fraction of the total mass. The rest is dark matter lurking unseen, but playing a crucial role in holding these clusters together. Despite all we've learned, dark matter remains one of the biggest mysteries in cosmology. Direct detection efforts, like those at the Gran Sasso National Laboratory and the Sudbury Neutrino Observatory, have yet to catch dark matter particles in the act. Indirect detection attempts, using instruments like the Fermi Gamma Ray Space Telescope to observe potential dark matter annihilations, have also come up empty. Theoretical challenges are just as daunting. We don't know the exact nature of dark matter, and its lack of interaction with electromagnetic forces makes it difficult to study. Well, the universe is so deep and mysterious that it seems impossible for us to explore it all. But humans are getting pretty advanced these days. We've managed to dodge the dark matter and see beyond it, discovering some incredible things. One of the most mind-blowing discoveries is the cosmic web, the large-scale structure of the universe. This vast network of galaxies and dark matter, separated by enormous voids, is like the universe's backbone, shaping the distribution of matter on the largest scales. First, let's talk about galaxies. They are the fundamental units of the cosmic web, collections of stars, gas, dust, and dark matter all held together by gravity. They come in all sizes, from small dwarf galaxies with a few billion stars to giant ellipticals with trillions of stars. There are several types of galaxies like spirals, think Milky Way, ellipticals, and irregulars. Each type has its unique role in the cosmic web, contributing to its overall structure and evolution. Next up are galaxy clusters, which are essentially groups of hundreds to thousands of galaxies bound together by gravity. These clusters are among the most massive structures in the universe, weighing up to 10 circumflex 15 times the mass of the Sun. But it's not just galaxies in these clusters. They also contain hot gas that emits X-rays and a significant amount of dark matter, which makes up the majority of their mass. Now, imagine the filaments of the cosmic web as cosmic highways. These thread-like structures connect galaxy clusters, forming the skeletal framework of the cosmic web. They can stretch over hundreds of millions of light years and contain a mix of galaxies, gas, and dark matter. Filaments play a crucial role in the growth and evolution of cosmic structures by channeling matter into galaxy clusters. On the flip side, we have voids, which are like the deserts of the universe. These are large, empty spaces between the filaments and clusters, making up about 80% of the universe's volume. Voids are regions with very few galaxies and low matter density. As the universe expands, these voids grow larger, pushing galaxies into the dense filaments and clusters. One of the most fascinating discoveries in this cosmic web is the Hercules Corona Borealis Great Wall. Discovered in 2013, this massive structure spans over 10 billion light years and consists of a huge cluster of galaxies and superclusters. Its sheer size challenges our understanding of the universe's scale and the distribution of matter, stretching across a significant fraction of the observable universe. There are other notable structures too, like the Sloan Great Wall, which was discovered in 2003 and spans 1.37 billion light years. It was the largest known structure at the time. Then, there's the Boots Void, an enormous void with a diameter of approximately 330 million light years, containing very few galaxies compared to surrounding regions. These colossal structures raise important questions about the uniformity of the universe and the validity of the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. Understanding these structures helps astronomers learn about the processes that shaped the early universe and the role of dark matter in galaxy formation. Mapping and studying the cosmic web involves several methods. The Sloan Digital Sky Survey, SDSS, has created detailed 3D maps of the universe, covering over 1/3 of the sky and cataloging more than 930,000 galaxies. By measuring the redshifts of galaxies, SDSS determines their distances and positions in the universe, allowing scientists to map the cosmic web in unprecedented detail. The Cosmic Microwave Background, CMB, provides early universe clues. Observations of the CMB, particularly by the Planck satellite, give information about the density fluctuations in the early universe that seeded the formation of the cosmic web. Tiny variations in the CMB's temperature reveal the initial conditions that led to the large-scale structures we see today. Gravitational lensing is another key method. This is the bending of light by massive objects, helping to map the distribution of dark matter in the universe. Projects like the Hypersuprime CAM survey use weak lensing to study the large-scale distribution of dark matter and the structure of filaments and clusters. Advanced cosmological simulations, such as the Millennium Simulation and Illustris, model the formation and evolution of the cosmic web over billions of years. These simulations are compared with observational data to refine our understanding of the physical processes driving the growth of cosmic structures. The cosmic web supports the idea that the universe is homogeneous and isotropic on the largest scales, providing a framework for the standard model of cosmology. It also offers crucial evidence for the existence and properties of dark matter and dark energy, which together make up about 95% of the universe's total mass energy content. The position of a galaxy within the cosmic web influences its properties, such as star formation rate and morphology, highlighting the importance of the large-scale environment in galactic evolution. As the cosmic web evolves over time, galaxies and clusters merge and grow, providing insights into the history and future of the universe. Observations of the cosmic web also contribute to our understanding of dark energy, the mysterious force driving the accelerated expansion of the universe. Models of the cosmic web help predict the ultimate fate of the universe, including scenarios such as the Big Freeze, where continued expansion leads to a cold, diffuse universe. When scientists were poking around deep space, they stumbled upon something pretty terrifying, and they termed it as entropy. Now, entropy might sound like some highbrow concept, but it's really just a measure of disorder or randomness in a system. It's a big deal in thermodynamics and has some profound implications for our universe. Essentially, entropy explains why things go from organized to chaotic and plays a crucial role in shaping cosmic events. So, what exactly is entropy? It's a thermodynamic quantity that quantifies how many ways you can arrange the components of a system without changing its overall state. The second law of thermodynamics tells us that entropy in an isolated system never decreases. In the grand scheme of things, this means the universe is always moving towards more disorder. Entropy is why your room gets messier over time, not cleaner. In the universe, it helps explain why time flows in one direction and how we went from a neat, low-entropy state right after the Big Bang to the complex, high-entropy universe we see today, filled with stars, galaxies, and even more chaos. Historically, the concept of entropy was introduced by Rudolf Clausius in the 19th century, and Ludwig Boltzmann took it further. Boltzmann linked entropy to the behavior of atoms and molecules, giving us the famous equation. This means entropy is proportional to the logarithm of the number of ways W. You can arrange a system's microscopic components with being Boltzmann's constant. Fast forward to more modern times, and we've got Stephen Hawking showing us that even black holes have entropy and can emit radiation, leading to their eventual evaporation. Now let's see how entropy plays a role in the deep cosmic dance of star and galaxy formation. Star formation starts in cold, dense regions of molecular clouds. As these clouds collapse under their own gravity, they turn gravitational potential energy into heat, increasing entropy. When stars form, they often do so in spinning disks of gas and dust, which further increases entropy through the dissipation of energy. Galaxies, on the other hand, form through the gravitational collapse of matter in the early universe. This process also involves a huge increase in entropy as gas clouds condense and form stars. Within galaxies, the interstellar medium, ISM, is a turbulent place. Supernova explosions, stellar winds, and black hole activities all stir things up, redistributing energy and increasing entropy. Black holes themselves are entropy powerhouses. They have a lot of entropy because of the vast number of microscopic states associated with their event horizons. The Bekenstein-Hawking entropy formula, where E8 is the area of the event horizon and LEL_PTs is the Planck length, gives us a way to measure this. Black holes redistribute energy and entropy in galaxies through processes like accretion and jet formation, influencing the dynamics and evolution of their host galaxies. Then there's the ultimate cosmic bummer, the heat death of the universe. This is the theoretical endgame where the universe reaches a state of maximum entropy. All energy gets evenly spread out, and there's no thermodynamic free energy left to do anything interesting. It's a cold, dark, and lifeless scenario, but don't worry. It's estimated to be trillions of years away. As the universe expands, driven by dark energy, entropy increases. Galaxies drift further apart, the cosmic microwave background, CMB radiation cools, and gravitationally bound systems like galaxies and clusters become more isolated. Stars will eventually exhaust their nuclear fuel, leaving behind white dwarfs, neutron stars, and black holes, all contributing to the universe's overall entropy. Recent discoveries have provided more insights into how entropy shapes cosmic phenomena. The CMB, a snapshot of the early universe, shows a nearly uniform temperature distribution with slight fluctuations that evolved into the large-scale structures we see today. Precision measurements by satellites like Planck have refined our understanding of the early universe's entropy. Black hole entropy is another fascinating area. Theoretical and observational studies of Hawking radiation have provided insights into black hole thermodynamics. Observations of black hole mergers by detectors like LIGO and Virgo have confirmed aspects of black hole entropy through gravitational wave signatures. The ongoing research into the black hole information paradox explores how information and entropy are conserved in black hole evaporation, impacting our understanding of quantum gravity. Now, if we're talking about the chaos and absurdity that lies deep in space, it's impossible not to mention cosmic strings. These are the wild, hypothetical, one-dimensional topological defects that might have formed during the early universe's phase transitions. It's like the universe is cooling and expanding after the Big Bang, and in the process, it's like the universe's version of a bad hair day. Cosmic strings are predicted by various field theories, especially those involving spontaneous symmetry breaking. This is the same kind of weirdness you see in materials like liquid crystals or superfluid helium, but on a cosmic scale. Cosmic strings are essentially the universe's imperfections. They're thin, infinitely long, and incredibly dense, with energy packed along their length. Imagine a cosmic sewing thread, but instead of cotton, it's made of concentrated energy. These strings supposedly formed during the universe's rapid expansion when the fundamental forces, gravity, electromagnetism, weak nuclear and strong nuclear, separated from a unified force. This dramatic process, known as a phase transition, caused different regions of space to settle into different states, creating defects like cosmic strings. The idea of cosmic strings was first floated in the 1970s by physicist Tom Kibble. In the 1980s, the concept got even more interesting when researchers connected cosmic strings with grand unified theories and string theory. These connections suggested that cosmic strings could influence the large-scale structure of the universe. It's like discovering that the universe's wrinkles aren't just cosmetic, but play a crucial role in its formation. So, what role do cosmic strings play in the grand scheme of the universe? One exciting possibility is that they acted as seeds for the formation of galaxies and other large structures. As cosmic strings moved through the early universe, their immense gravitational pull could have attracted matter, creating density fluctuations that eventually formed galaxies. Essentially, these strings could be the unsung architects of the cosmos. Their gravitational effects could also produce unique lensing effects. Imagine light from distant objects bending around these strings, creating unusual patterns that we could potentially observe. These lensing effects would be different from those caused by regular celestial objects, appearing as line-like distortions, rather than the usual arcs or rings. Cosmic strings might also leave their mark on the cosmic microwave background, CMB, the afterglow of the Big Bang. These imprints could show up as discontinuities or temperature anomalies in the CMB, providing indirect evidence of their existence. Furthermore, some theories propose that cosmic strings could have formed at the end of the inflationary period of the early universe, contributing to the inflationary model's predictions about the universe's uniformity and structure. Detecting cosmic strings is no small feat, though. It's like looking for a needle in a cosmic haystack. However, scientists have a few tricks up their sleeves. One method involves gravitational wave detection. Cosmic strings are expected to produce gravitational waves as they oscillate and interact. Observatories like LIGO, Laser Interferometer Gravitational Wave Observatory, and the upcoming space-based detector LISA, Laser Interferometer Space Antenna, are on the lookout for these ripples in spacetime. Another approach is through gravitational lensing surveys. Astronomers search for the unique lensing effects caused by cosmic strings. These effects would stand out as line-like distortions, quite different from the arcs or rings caused by more familiar objects like galaxies. Observatories such as the Planck satellite and the upcoming Simons Observatory also analyze the CMB for anomalies that could indicate the presence of cosmic strings, focusing on high-precision measurements of temperature fluctuations and polarization patterns. Radio telescope arrays like the Square Kilometer Array, SKA, could detect radio emissions or transient phenomena associated with cosmic strings. These observations might include bursts of radiation from cosmic string loops or cusps, giving us more clues about their existence. Discovering cosmic strings would be a game-changer for our understanding of the universe. It would validate key aspects of high-energy physics theories, including guts and certain models of string theory. Confirming their existence would also support the idea that phase transitions occurred in the early universe, leading to the formation of topological defects. Well, cosmic strings might be tough to see for everyone, requiring a ton of math and some fancy equipment. But buckle up, because what I'm about to tell you is way more complex than cosmic strings. There's a type of star called Wolf-Rayet stars with boxy ripples. Yeah, it sounds fancy and kind of cool, but these stars are even more terrifying and dangerous than wolves on Earth. Wolf-Rayet WR stars are among the universe's most extreme and fascinating objects. Named after French astronomers Charles Wolf and Georges Reye, who first spotted them in the 19th century, these stars are massive, hot, and wild. They're the rock stars of the stellar world, burning bright and living fast. These stars are giants, typically 20 to 50 times more massive than our sun and up to 1,000,000 times more luminous. Imagine our sun. Now think about something 50 times bigger. Hard to wrap your head around, right? It's almost too much for our human brains to handle. They're in a late stage of stellar evolution, meaning they're on their way to exploding as supernovae or producing gamma-ray bursts. Their surface temperatures are insane, ranging from 30,000 to over 200,000 degrees Kelvin. To put that in perspective, our sun's surface temperature is a mere 5,500 degrees Kelvin. Wolf-Rayet stars are like cosmic blowtorches, but it gets crazier. Wolf-Rayet stars have incredibly powerful stellar winds, blasting away at speeds up to 3,000 kilometers per second. These winds are so strong they strip away the star's outer layers, exposing its hot and dense core. If you think Earth's weather is wild, imagine being near a Wolf-Rayet star. It's like being in a hurricane of hot plasma all the time. The spectra of these stars are also unique. Instead of the usual absorption lines, their spectra are dominated by broad emission lines of ionized helium, nitrogen, carbon, and oxygen. This is due to their dense and fast-moving winds creating shock waves in the surrounding material. Now let's talk about one of the coolest Wolf-Rayet stars out there, the R140. This star system is about 5,000 light-years away in the constellation Cygnus and has gained fame because of its unusual boxy ripples. WR140 isn't just one star, but a binary system, meaning it's a pair of stars. One of them is a Wolf-Rayet star, and the other is an O-type star, and they're in a highly elliptical orbit around each other. This leads to some wild interactions. So what's the deal with the boxy ripples? These structures form because of the periodic collision of the stellar winds from the two stars. Every time the stars come close in their orbit, their winds smash into each other, creating these distinct boxy-shaped shells or ripples. High-resolution infrared observations from instruments like the Keck Observatory and the Very Large Telescope, VLT, have captured these incredible details. The dust produced in these collisions is pushed into geometric shapes, making WR140 look like it's wrapped in a series of expanding boxy shells. This binary system's orbit takes about 7.94 years to complete, meaning the colliding winds and dust production happen in a predictable cycle. It's like the universe's version of a cosmic clockwork, with these dramatic events occurring regularly. Studying WR140 and its boxy ripples gives us valuable insights into the complex interactions between massive stars and their environments. These findings help us understand how stellar winds collide and the effects they have, such as increased mass loss rates and unique dust formations. This dust eventually gets recycled into the interstellar medium, contributing to the material that forms new stars and planets. Wolf-Rayet stars are also important for predicting supernovae in deep space. By studying these stars and their mass loss processes, astronomers can better understand the conditions leading up to their explosive deaths. Additionally, the strong winds and periodic dust ejections influence the surrounding interstellar medium, potentially regulating star formation in nearby regions. The study of Wolf-Rayet stars like WR140 is far from over. Future observations with more advanced telescopes like the James Webb Space Telescope will provide even clearer images and more detailed spectral data. This will help us understand the processes driving the formation of boxy ripples and other stellar wind structures. Improved computational models will also aid in simulating the complex interactions in our binary system, predicting the behavior of stellar winds and the resulting structures. Observations across different wavelengths, from X-rays to radio waves, will give us a more comprehensive picture of the physical conditions around these stars. By understanding the mass loss processes in Wolf-Rayet stars, astronomers can better grasp their contributions to the chemical enrichment of galaxies. The heavy elements produced and ejected by these stars play a crucial role in the formation of planets, and eventually life itself. I know it's hard to believe that something like Wolf-Rayet stars exist, being 50 times bigger than the sun. But just when you think space can't get any crazier, we stumble upon something that's 50,000 times the mass of our sun. Yep, you heard me right. We're talking about a record-breaking black hole that has astronomers everywhere doing a double take. This cosmic heavyweight is located in the dwarf galaxy RGG 118 and is the smallest supermassive black hole ever observed, weighing in at a mind-boggling 50,000 times the mass of our Sun. This black hole in RGG 118 was found about 340 million light-years from Earth. What's really interesting is that it's hanging out in a dwarf galaxy. These galaxies are usually much smaller and less flashy than their spiral or elliptical cousins, which makes this discovery all the more intriguing. Despite being the runt of the supermassive black hole litter, this little guy behaves just like its bigger siblings. It gobbles up material and spits out X-rays, challenging what we thought we knew about black hole growth and evolution. The Chandra X-ray Observatory was key in spotting this black hole, thanks to its ability to detect X-rays from the hot gas surrounding it. Meanwhile, the Very Large Array, VLA, helped by providing more data about the black hole's environment. Together, these observatories painted a picture of a black hole that, despite its smaller size, still packs a serious punch. So, why is this tiny titan so important? Well, finding such a small supermassive black hole in a dwarf galaxy forces us to rethink our models of black hole formation. Traditional theories suggest that supermassive black holes grow by eating lots of gas and merging with other black holes over time. But this little guy suggests there might be other ways for black holes to bulk up. One theory is that black holes can form from the remnants of massive stars early in the universe's history. These are known as seed black holes. The discovery of the black hole in RGG 118 supports the idea that these seed black holes can exist in a variety of galactic environments, not just in the big, flashy galaxies. This could mean that supermassive black holes are more common than we thought, even in the smallest galaxies. Understanding how black holes of different sizes interact with their host galaxies is crucial for figuring out how galaxies evolve. This discovery shows that even dwarf galaxies can have black holes that play a big role in their dynamics and evolution. The Chandra X-ray Observatory has been a game changer in black hole research. By detecting X-rays from the hot gas around black holes, Chandra allows scientists to spot these cosmic beasts even when they're hiding in distant galaxies. Its high resolution and sensitivity mean it can pick out faint X-ray sources that other telescopes might miss. And when you combine Chandra's data with observations from other telescopes like the VLA and the Hubble Space Telescope, you get a fuller picture of these enigmatic objects. The discovery of this tiny, supermassive black hole in deep space opens up a lot of exciting possibilities for future research. The James Webb Space Telescope, JWST, set to launch soon, will have even greater sensitivity and resolution, enabling the discovery of more small supermassive black holes in dwarf galaxies. Large-scale surveys like those conducted by the Sloan Digital Sky Survey, SDSS, will keep identifying potential black hole candidates in a variety of galactic environments, giving astronomers a broader sample to study. Theoretical models will also need to evolve to incorporate new data from these discoveries, leading to a more nuanced understanding of black hole formation and growth. Researchers will explore alternative formation scenarios, including direct collapse models and the role of dark matter in black hole formation. And let's not forget multi-messenger astronomy. The integration of gravitational wave observations with electromagnetic observations will provide a more complete picture of black hole mergers and growth processes. Instruments like LIGO and Virgo, which detect gravitational waves, will complement X-ray and radio observations, offering new insights into black hole dynamics. But enough about black holes for now. Let's talk about how stars are born in galaxies in the deepest part of space. Well, star formation mainly happens in these super chilly regions called cold molecular clouds. Think of them as the universe's nursery rooms filled with gas and dust. These molecular clouds, often nicknamed stellar nurseries, are made mostly of hydrogen molecules. And get this, they're freezing cold, typically around -263 to -253 degrees Celsius. These cold molecular clouds are like the universe's baby factories, pumping out new stars left and right. They have low temperatures and high densities, which make the perfect environment for gravity to do its thing. Gravity can overcome thermal pressure and cause the gas to collapse, leading to star formation. It's like nature's way of making sure the next generation of stars gets a good start. The whole process kicks off with gravitational collapse. A part of the molecular cloud starts to shrink under its own gravity, breaking into smaller pieces. Each of these pieces can form one or more stars. Sometimes external events like shockwaves from supernovae or collisions between clouds give the process a little nudge. As the gas continues to collapse, it forms a protostar in the center. This baby star keeps growing by pulling in more material from its surroundings. The core temperature rises until nuclear fusion ignites, and bam! A new star is born. Dust and heavier elements within these clouds help cool the gas, making it easier to collapse and aiding in the formation of planetary systems around these newborn stars. Now let's talk about the Atacama Large Millimeter Submillimeter Array, ALMA. This telescope has given us incredible insights into star formation in the early universe. By observing cold gas in distant galaxies, ALMA helps us understand how galaxies formed back in the day. ALMA's high-resolution imaging allows astronomers to see the detailed structure and dynamics of molecular clouds in galaxies. This has led to discovering complex gas distributions and star-forming regions both nearby and far away. Observations of distant galaxies show that cold gas was abundant in the early universe, indicating that star formation was a vigorous process soon after the Big Bang. For instance, ALMA has observed massive reservoirs of cold gas in early galaxies, showing that these galaxies rapidly built their stellar populations. This supports the idea that large galaxies formed by quickly gathering cold gas, fueling intense star formation. ALMA has also detected powerful molecular outflows in some galaxies, driven by star formation and active galactic nuclei, AGN. These outflows can regulate star formation by expelling gas from galaxies, playing a crucial role in their evolution. Let's check out some specific galaxies where cold gas is driving star formation. Take NGC 253, also known as the Sculptor Galaxy. ALMA's observations reveal detailed structures of cold molecular gas in its central starburst region, showing that the galaxy's intense star formation is fueled by dense molecular clouds, collapsing to form new stars rapidly. Then there's the Spiderweb Galaxy, observed at a redshift of 2.16. This galaxy is an example of a protocluster in the early universe. ALMA detected large amounts of cold gas in the galaxy, indicating it's in a phase of intense star formation, potentially leading to the formation of a massive galaxy cluster. And let's not forget Cosmos Aztec 1, located at a redshift of 5.3. ALMA's observations show this galaxy has an exceptionally high rate of star formation, driven by a massive reservoir of cold gas. It's forming stars at a rate 1,000 times that of the Milky Way. Understanding cold gas and its role in star formation has significant implications for our understanding of galaxy evolution. Cold gas fuels star formation, explaining the star formation rates observed in different galaxies across cosmic time. It's a critical factor in the growth and development of galaxies, allowing them to build up their stellar masses and evolve into more complex systems. We've ventured far into deep space, uncovering all sorts of cosmic wonders. But what if I told you that one of the most mysterious places is right in our cosmic backyard, near Jupiter? That's right, we're talking about Europa, one of Jupiter's largest moons. This icy world is more fascinating than anything we've discussed so far. You might ask why, it's just a moon, isn't it? Well, Europa is no ordinary moon. It's about 3,100 kilometers in diameter, slightly smaller than Earth's moon, but it's hiding some big secrets under its icy surface. Imagine a vast subsurface ocean covered by a thick shell of ice. This ocean could be teeming with the building blocks of life, making Europa a prime candidate for the search for extraterrestrial life within our solar system. The smooth, bright surface of Europa is made mostly of water ice and has fewer craters than other moons, suggesting it's constantly being reshaped by geological activity. So, what's keeping Europa's ocean from freezing solid? It's all thanks to the gravitational interactions with Jupiter and its fellow moons, Io and Ganymede. These interactions create tidal flexing, generating internal heat within Europa. This heat keeps the subsurface ocean in a liquid state, despite the moon's distance from the sun and its frigid surface temperatures. Europa's potential for life is what really gets scientists' pulses racing. The combination of a subsurface ocean, internal heating, and essential chemical elements creates a potentially habitable environment. Scientists think there could be hydrothermal vents on the ocean floor, similar to those on Earth. These vents could provide the necessary energy and nutrients to support microbial life. The Galileo mission, which orbited Jupiter from 1995 to 2003, gave us our first big clues about Europa's secrets. Galileo detected a weak magnetic field around Europa, likely caused by a salty ocean beneath the ice. High-resolution images showed a surface crisscrossed with ridges, bands, and chaotic regions, suggesting a dynamic icy shell with tectonic activity similar to Earth's. The Juno spacecraft, currently studying Jupiter, has also provided valuable data about Europa. It's helped refine our models of Europa's interior structure and observed variations in ice composition and thickness, hinting at ongoing geological processes. One of the most exciting discoveries is the potential presence of water vapor plumes erupting from Europa's surface. Both Galileo and the Hubble Space Telescope have suggested these plumes, which could offer a way to sample the subsurface ocean without having to drill through the ice. Looking ahead, the Europa Clipper mission, set to launch in the 2020s, aims to get up close and personal with Europa. This mission will carry a suite of scientific instruments to analyze the moon's ice shell and subsurface ocean. One of its main goals is to search for biosignatures, indicators of life, or its precursors, by analyzing the composition of the surface and potential plumes. The Europa Clipper will use advanced technology to navigate Jupiter's harsh radiation environment and conduct high-resolution mapping of Europa's surface. These innovations will pave the way for future missions, potentially including landers or even subsurface probes to explore Europa's ocean directly. Exploring Europa and other icy moons has huge implications for understanding habitability in the solar system. These missions challenge our assumptions about where life can exist. Traditionally, the habitable zone is thought to be where liquid water can exist on a planet's surface. But Europa shows us that subsurface oceans, kept warm by internal heat, can also be potential habitats. And since we've journeyed through the deepest, darkest corners of space, now it's your turn to spill the beans. What's your deepest, darkest secret?